large generation of energy through that process. Brown dwarfs don't have that going on. And as a result, a brown dwarf just cools and fades over time. So young brown dwarfs could look similar to low mass stars and have temperatures of perhaps 2,000 or 3,000 Kelvin. But as brown dwarfs age and become a few billion years old, the situation
looks
changes.
Like we're blessed.
Degrees to just a few hundred degrees, and even tens of degrees. So you can have brown dwarfs with atmospheres that are similar temperature to the atmosphere of the Earth.
So do they just form on a spectrum with the different types of stars leading down into the gas giant type planets? Or is there something very particular about the conditions in which they form or the materials that they form from that gives them these properties?
Not specifically, really. The formation of brown dwarfs is quite a complex issue. It's not really clear if the brown dwarfs that we see and identify as brown dwarfs actually formed like stars, or whether some of them formed in ways more similar to the way that planets form. You can't really turn the clock back and watch in detail how the object forms. And it can be very difficult to infer how it's formed by measurements that you can make on very faint objects. So my feeling is that the provenance of the brown dwarf population is quite diverse. And in that sense, it's a different situation to stars because we kind of know how stars form. And when we look at planets, at least including our own solar system planets, we kind of have a reasonable idea how these would form as well. So brown dwarfs, although they have fairly simple structures, they have quite a complex and likely diverse origin.
We can also learn a lot about the bigger, hotter stars from the ends of their lives where they explode in supernovae. What happens at the end of the life of a brown dwarf?
So really, brown dwarfs don't have an end to their life. One might think of a brown dwarf as an immortal star in that sense. So they just continue to cool and fade with time. You might have a brown dwarf that started life with a temperature of perhaps 3,000 degrees, and by the age of the sun, it had cooled to perhaps 300 degrees. In many billions of years' time, it could have cooled to a few tens of degrees, and eventually it will cool to a point where it becomes almost invisible, and you can't really see it. So at that point, you kind of have a dark star. But they never actually end their lives in the kind of impressive display that you see from supernovae or planetary nebulae. So in that sense, or planetary nebulae. So in that sense, they just go on.
You've brought up an interesting point there by saying that as they get colder, they essentially get harder to spot. What are the problems with looking for these cold objects out in space?
There's two problems, really. Cooler objects have much fainter luminosity, and also cooler objects emit longer wavelengths of radiation. So if you have extremely faint, extremely cool objects, you have to look at quite long wavelengths, and you have to have a very sensitive telescope. Now, in the infrared, for instance, in order to be able to measure anything at all, mid-infrared wavelengths, for example, you have to be above the atmosphere, because the Earth's atmosphere glows with infrared light and also blocks out many wavelengths of infrared light. And so, unless you put your telescope above that atmosphere, then you can't. So that's a very difficult and challenging and expensive thing to do. And particularly if you're wanting to put a very large telescope above the atmosphere in order to detect these extremely faint things, then the two problems together really spell out a scientific and a financial challenge.
And how are we actually doing with spotting these? Much like exoplanets, it seems that we didn't see any of them until barely a few years ago, and now they're in very large numbers. How are we doing it?
The discovery of large populations of these objects is very much governed by the availability of new technology. So the reason that we found dozens and now several hundred warm brown dwarfs in the past few years is because we've had improvements in ground-based CCD technology, allowing us to detect these things not only at optical wavelengths but also importantly in the near infrared. And with the recent launch of the WISE satellite, the mid-infrared all-star survey, this has allowed us to identify the new population of white dwarfs, albeit only half a dozen. White dwarfs, albeit only half a dozen at the moment. But by making use of this new technology, these are going to be turning up in significantly larger numbers in the coming couple of years.
And what scientific questions do you think we'll be able to answer once we find more of these and probe them and learn more about their properties?
One question I find particularly interesting is what happens when you get water droplet clouds forming in the atmosphere of brown dwarfs. The coolest brown dwarfs at the moment, known as white dwarfs, they have very strong ammonia. They also have very strong water vapor. In the future, if we move down to even cooler temperatures, we would expect to see water droplet clouds, or rain, if you like, condensing out in the atmospheres of these objects. This would most likely require a new additional spectral type, even beyond the white dwarfs. But I think that understanding the physics of how these rainy, really cool atmospheres work, this will be important not only in terms of understanding the physics of brown dwarf populations, but also in trying to understand how extrasolar giant planets, how their atmospheres work, and in turn using that knowledge to measure the properties of future planet populations.
David Bigfield from the University of Hertfordshire. Finally for this month, the Missing Astrofest talk. Former Member of Parliament Levit Opik sadly had to pull out of Astrofest at the last minute, so he missed out on his opportunity to explain why space fascinates him.
I became interested in astronomy because my grandfather was a professional astronomer, and you can really see that people reading Janet and John books, I was reading The Oscillating Universe, and quite literally from the age of 45, I was already discussing with my dad where we came from in the galactic sense, and I was very up to speed with Big Bang Theory by about the age of 10, and I remember that quite clearly.
And you have allowed this interest to spill over into your professional life as well, in that you're now campaigning about what you see as a very serious issue. Tell me a bit more about that.
My think it should be called the open cloud, or at least your big cloud, a compromise on that. And that's important because he was also a pioneer of the idea that the Earth had been hit by asteroids and comets many times in the past, and that it was still happening. People thought it was a cranky idea at the time, but actually scientists caught up with that. So I chose to carry on the same sort of campaign when I was a member of Parliament, to try and get British politicians to invest in British astronomy to basically safeguard ourselves from what is literally a catastrophic global threat.
We know that asteroid impacts have definitely happened in the past. We see evidence all over Earth, even more evidence on the moon. Of course, we have not eroded away. But it very much seems like a distant threat, something that... It's like a distant threat, something that happened in the past, might happen in the future, but I don't think there's any fear of it happening again. Should we be frightened?
Most people aren't concerned about asteroid impacts. They don't phone up their boss at work and say, I'm not coming in today because I'm a little bit depressed about Tunguska, which is a fairly famous example of an impact not so long ago. They should be concerned because these things don't happen very often, maybe less often than they did in the past as the solar system cleaned itself out a bit, but they still happen. They're actually 750 times more likely to die as a result of an asteroid impact into the national lottery in any given weekend, and since somebody's just won £45 million, they should be pretty concerned.
So what are you proposing that we should do? I assume you need the scientists and politicians to get involved so that we can approach it.
Hey, Lubot.
My expectation, if you like, my demand, my requirement is twofold. The politicians need to fund some serious investment in tracking these objects, and then the astronomers need to be given the space to do the right thing. And the irony is, I convinced the government to do a report on this, called the Near Earth Object Task Group Report on Near Earth Objects, not so over a decade ago, thinking about it. Of the 14 recommendations in the government's own report, they've actually implemented half of them. So if
There's a flashing yellow light outside my window for some reason.
if London becomes a
Hell,
symbol
it
of
is.
influence by our politicians.
So if you could give me an example of some of the 14 recommendations that you put forward.
The key recommendations
That's a tow truck.
Once again, I stress a government-sponsored report were to invest in public
There's
information.
a tow truck outside.
Citizens of Britain to understand the issue better, to work internationally on telescopes, which would rocket science in a literal sense, to track these objects. Thirdly, to really quantify the threat and make sure that in the event of some object being identified as going on. As I say, half of one of those was implemented. A little bit of money was given to the British National Space Centre, but nothing to Space Guard UK, for example, a dedicated organisation run by Jay Taylor to work on this. And I think that that's responsible.
So just going back to the alternative, if you prefer, how does that tie into near Earth objects? You know the Oort cloud is there, we know it's a long way away, we've got a reasonable idea of what it's made of, but it doesn't actually send things towards us on a regular basis. So what's the link between the two?
The reason I was at the Astrofest conference is to discuss whether the Oort cloud is in fact the great, dark, untalked about threat in the solar system. My grandfather postulated that there are as many as a million, that's a trillion objects there. Perhaps sometimes when a passing nearby star gives the Oort cloud a shake, we get a massive bombardment of these objects here in the solar system. That's very, very bad news for life on Earth, because Jupiter, which sometimes sweeps these objects up as they come into the central solar system, wouldn't be able to handle all of them. And that's really got problems. So we need to understand the Oort cloud, as I like to call it, and I certainly think more than that, to understand whether there's a clear and present danger from there. But more than anything, we have to be able to observe our nearby solar system so that we are prepared. Seeing it 6 months before it is, it's way too late.
A little bit opaque on the threat of near Earth objects. And that's it for this Astrofest special. Join us next time for more space science news, interviews, and answers to your questions. And keep your comments and questions coming in by email to us at thenakedscientists.com. You can follow The Naked Scientists on Twitter, that's The Naked Scientists, or join us on Facebook, facebook.com/thenakedscientists. Naked Astronomy is produced by me, Ben Balzer, and comes to you from Cambridge University with support from the Science and Technology Facilities Council.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientists.com/astronomy.
Can a girl ever enjoy too much glam? Can a girl ever enjoy too much glam? Kmart doesn't think so. We've got your glow covered with all your She Glam babes and the latest drops. Think flawless all-day beauty, bold, fun, striking colours, dream blushes, gorgeous shades, perfect primers, and luscious lips. Pure glam, no gimmicks, and 100% cruelty-free. It's makeup your skin will love. Explore the full She Glam range today. Shop in-store, online, and via the Kmart app. Kmart, low prices for life.
With the Bank West single-use virtual card, your card details disappear after use, which means less time worrying about fraudsters and more time worrying about sleep, alternative milks, captcha screens, and having to talk to other parents. Bank West, just enough bank. Eligibility criteria apply. Consider the TMD and PDS or TNCs available from Bank West. Thrusting space science into the audio dimension. This is Naked Astronomy.
How do tornadoes form on the sun? Why does Jupiter enhance our meteor showers? And how can pulsars be used as a deep space positioning system? This month's Naked Astronomy comes from the Royal Astronomical Society's National Astronomy Meeting, held this year at the University of Manchester. We'll hear how Juno goes probed beneath the surface of Jupiter. We'll find out how a cloud of carbon gives us clues about star formation in the early universe, and we'll explore how astronomers have helped
Wicked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Juno is NASA's mission to Jupiter, launched in August 2011, and only last month it successfully made fine adjustments to put it on course to reach the planet in July 2016. But in a time when astronomers are seeing further back than ever before and spotting exoplanets and even whole extrasolar planetary systems, why should we be putting Jupiter at centre stage? To find out, I spoke to Professor Frank Bagenol from the University of Colorado.
To understand how our solar system formed, we need to know how the biggest member formed as Jupiter. So it has a lot of the mass of the planets. It's the biggest planet. It pushes things around. If we don't understand how Jupiter formed, we actually have a really hard time explaining how the solar system formed. And if we can't explain our solar system, then I don't think we have a lot of good explaining for other solar systems. So indeed, these things are all linked. We've been finding Jupiters, similar-sized planets on stars. They're in very different places. So this is a big question. We tend to be closer to the star, and this is partly because that's what we can see. But we need to find out how solar systems form. Are they different in the way that they form? Is it just in sheer timing? Or is it just they're structurally radically different? So we need to understand those first. And the biggest problem we have right now is that our current grand idea of how solar systems form is up in the air. Questions are being raised because of the Galileo probe going into Jupiter's atmosphere and finding a lot less water than we would have expected. And that has raised questions about our whole idea of how the solar system forms.
So what are the big outstanding questions about Jupiter itself?
So we want to know the amount of water inside Jupiter. Most of Jupiter is actually hydrogen gas, the dominant element of the universe. The third most abundant element of the universe is oxygen, which forms with hydrogen and water. And so our idea of how the solar system formed is that beyond a certain distance, the snow lumps of ice formed, condensed, came together, bumped into each other, and formed big snowballs. And those huge snowballs, many times the mass of the Earth, in fact, was able to pull in hydrogen to make the big gas giants. But if we don't know the amount of water in the original nebula or in Jupiter, then we don't have much hope of this theory.
So what is the structure inside Jupiter? If we were to slice it apart, what would we expect to see?
Well, we know that as you go deeper down in the ocean, the pressures get greater. But inside Jupiter, we have the same thing. The pressures get deeper and deeper down you go. So hydrogen gets compressed, and at some point, it goes from being this clear gas to a liquid that is metallic. So it's more like mercury, the liquid metal mercury inside the deep interior. What we don't know is that original core of about 20 to 30, sometimes 15, but some numbers between 15 and 30 Earth masses of ice. Is that a core, a solid core at the centre, or has it been sort of mixed up with hydrogen in there? So what we want to find out with Juno is there a strong concentration of mass at the centre, or is it a more gradual distribution of hydrogen?
And what's Juno actually going to do? How's it going to achieve that?
Well, what we do is we use the spacecraft as a sort of test bed. It's like dropping a hammer, or like Galileo dropping balls from the Tower of Pisa. We're going to effectively drop Juno around Jupiter and measure how fast it moves. What we're actually going to measure are very small perturbations in its capacity around Jupiter by using the Doppler shift of the signal that it sends back to Earth. So we have a very carefully calibrated radio signal dish that sends back signals. We detect those on the ground, and the small Doppler shift, the rising and lowering the frequency of that radio signal, will give us a clue about small changes in speed of the spacecraft as it goes past Jupiter.
I think we've done something similar around Earth, measured changes in Earth's gravitational field, and that's given us some very interesting information about density difference in the Earth. So are we looking more than just gravity, though? Are we trying to actually probe the contents and see if that mixing is occurring in a more direct way without just looking at how it attracts Juno itself?
It's very similar to the GRACE mission around the Earth and the mission to the Moon. It's much less sophisticated, unfortunately, because we only have one spacecraft, two in each case. But it's the same principle. And indeed, that only gives us the gravity field. We will also measure the magnetic field, and that's important because that gives us where the domain is produced and some sense of the structure of the magnetic domain deep inside. We will also measure the amount of water in the upper layers of the atmosphere using very clever technique, microwave sensing. So the idea there is the deep interior is hot, it's glowing in the microwave region. And what we then do is we measure the amount of those signals that are absorbed as they come out through the clouds, through the gases, the outer layers. And that will tell us the distribution and the amount of water that's in the outer layers of Jupiter. So we get some clue on composition, we get some clue on density, distribution, mass. We put that all together with our theories and some sense of how hydrogen behaves at these pressures and temperatures, the equation of state. Will hopefully help us work out what's going on.
Jupiter also has a fine and varied collection of interesting moons that presumably feed back into the planet itself. How are you going to tease apart the influence of the moons when you're looking at the gravitational data?
So there are tides raised on Jupiter, just as we have tides on Earth raised on Earth. And we will look for those tides. But just as our tide comes and goes with half the stability pretty much of Earth, we're going to have the same thing happening with the order periods of the moons around Jupiter. We'll be able to look at those frequencies that will tell us what's caused by the moons and what's caused by the internal structure. So with 20 orbits, I think over a period of 18 months, we'll be able to tease out those different effects.
Seeing as you're sending these instruments out there anyway, can you not also have a look at the moons while you've got it there?
Well, we've designed our because we have to do two things. We have to close the planet, and we have to avoid the deadly radiation fields. There's a sort of donut of very, very high energy electrons that are trapped in sphere around the equatorial belt of Jupiter. So we have to duck under those over the poles. And so this means that our orbit is mostly in the above and below the equatorial plane, but the moons are in the equator. So we're in the wrong place. We're going to the wrong place to look at the moons. However, because of the fact that Jupiter is rather tubby, it's fatter around the equator than it is around the poles, this tugs on the orbit and changes the orbit. And so eventually, halfway through, towards the end, we will be crossing the orbits of Callisto.
14 kilos, huh?
So we may get a chance to have a quick glimpse of those.
Alrighty.
Can we use some of what we'll see in Jupiter to get a better idea of how Jupiter has aurora just like we do? Is this going to be a good test of our theories that we apply to Earth?
Absolutely.
That's
I've always said that we can never have true confidence that we really understand how basic quantum physics works in the auroral region and the space environment of Earth until we tested those theories elsewhere. And I would, because I'm interested in going elsewhere. But in truth, we are applying our theories developed from the many satellites that have orbited the Earth's environment and use those theories and those models and predictions for the very data around Jupiter. Some of them are similar, some of them seem to be different. So we're having a good argument about these issues in our field, about exactly how it all works and fits together. And we hope Juno will tell us the truth.
Frank Bagenal from the University of Colorado. Even before Juno gets to Jupiter, we're developing a better understanding of how the giant planet affects the rest of the solar system. Ashwin Shakur at Lamar Observatory in Northern Ireland looked at how Jupiter's enormous gravitational influence may alter the flight of Halley's Comet. And because the tail of the comet produces both the Orionid and the Eta Period meteor showers, it can also alter meteorites from Earth.
The problem we're looking at is why do we have different meteorites in different years in the case of Orionus, or for that matter, in why don't we have uniform meteorites in every year? We found out that the periodic effects from Jupiter is that it's at different rates for enhanced meteorites in some particular years.
Most meteorite showers that we see on Earth are the result of Earth moving through an existing cloud of rockets and bits left over comet. So the question you're asking is why isn't that the same every time we move through it? What does Jupiter do?
Usually when a comet outgasses, that is, when the particles go out of the comet, it spreads uniformly along the whole orbit. But when you have some particular periodic gravitational effects from Jupiter, that would make those outgassed particles cluster together rather than getting spread over the whole orbit. So that makes sort of bunches of particles or sort of clusters. And when the Earth moves through such clusters, it encounters more number of meteors, which we call as meteor bursts.
What's the mechanism for causing it, Roger?
When Jupiter and the comet precisely coincides in some particular positions, there's a particular gravitational effect, or you could say a small kick from the Jupiter, which actually corrects or constrains it. So that's the difference. When this occurs on the comet, then the particles which outgasses, they will also encounter the same effect. So when a comet itself is in resonance, so that's the scientific name we call for such a meteoroid, you have more chances of the meteoroids becoming resonant. So such meteoroids cause meteor outbursts. So precisely knowing the history and of the comet itself is very important for understanding the evolution of meteor stream.
So they fall into resonance with each other just as a result of the clockwork nature of our solar system. How have you actually been studying this? What have you been looking at?
So we were trying to look at particles which are similar to the orbit of the comet. So that's the whole point, because all these particles get outgassed from the comet. So all of them have similar orbits. So that's how we do theoretical simulations of meteor streams of any comet. So then we were trying to look at the future of these meteoroids or these dust particles from the comet, and we were trying to track them as to how they spread along the whole orbit. And we see that due to these effects from the Jupiter, they seem to bunch together rather than spread, which is essentially the reason why when the Earth goes through
So when will we be able to see this altered activity show?
there was a meteor outburst in 1993. Again, there was a meteor outburst in 2006 to 2010. So this particular outburst in 2006 sort of triggered many scientists to be the reason.
That felt heavy.
And eventually learning from those works, we were trying to simulate the comet and Orion's stream as well. So now we find that our results suggest that the 1993 outburst could be explained by a particular resonance mechanism of Jupiter. And now we could also extrapolate and say that in 2070 there will be a similar activity. And looking back at the historical records, in 1916 as well as 1950, we see hints of such enhanced meteorites. So all these previous observations fits perfectly with the model. So we think all these activity could be explained by these effects from Jupiter.
So what else can this tell us about the dynamic systems that exist in our solar system? Does this purely tell us about the meteor showers that we encounter on Earth, or can we learn more about it on a wider scale?
The most important point of resonances is that it really helps the celestial bodies to have a particular evolution or particular dynamics, so that it gets constrained in a certain sense. So it makes many planetary orbits more stable, many meteoroid orbits more stable. So overall resonances play a huge role in the solar system.
And presumably we can't see comets falling into resonance with other planets, but because they're so small, because they're not very massive, the effect is just too small to detect.
Yes, so the main point is the whole thing depends on how massive and how powerful the gravitational effects will be. So we could argue that there would be small resonance effects from Saturn, which is also quite massive, but not as massive as Jupiter. But as you said, these effects are very small or very negligible compared to the effects from Jupiter. So Jupiter's effect really overpowers all the other effects from the planet. So that's why we predominantly see the resonance.
Oh dear.
And can you now apply what you've learned to other comets and to other astronomical bodies to try and make
So we were trying to look for many other solar system bodies, a few other comets and a few other asteroids, and see whether they also fall into such resonance mechanisms. And the most interesting thing is, out of about 27 bodies, 14 bodies got trapped in such resonances in the past as well as future. So it seems to be very interesting. There are so many solar system bodies which would really get trapped in these resonances and all these effects could actually really work on other systems as well. So it seems to be a very general phenomenon.
Ashwin Chopra from Juno's route to Jupiter was carefully planned out.
It's another team.
A series of maneuvers, including a gravitational in October 2013. But as we push further out into the universe, we're going to need to rely on spacecraft that can find their own way. To navigate in open space. Professor Werner Becker from the Max-Planck Institute for Extraterrestrial Physics in Munich thinks we may have to rely on some strange astronomical objects.
Pulsars are highly magnetized and spinning neutron stars. And neutron stars are, in fact, the most compact objects that you can observe directly in the universe. Neutron stars are the compact remnants of massive stars when they end their life. The Sun, for example, will end in a white dwarf. And if you have stars 30 times or higher in mass than the Sun, these stars are expected to end their life in a big supernova explosion, which led to a neutron star, which is a compact object, a giant amount of nucleus, having a size of about 10 kilometers in radius, and a density which exceeds 80% of nuclear material.
Pulsars are recognizable for a regular radiation being radioactive. How can we take advantage of the fact that we do have this regularity?
First of all, there are a diversity of pulsars out there in the universe. They are called accretion-powered pulsars. They produce the light by material falling onto neutron stars. They are magnetized, really huge, extremely magnetic fields, and both of them exhibit bursting light flashes. And you see their rotation, this periodicity just in this burst, which is still unregular because this source is not bursting just time after time, not really predictable when they burst. So there's just one group of pulsars which can be used for navigating spaceship in the universe, and these are the so-called rotation-driven pulsars. So these pulsars have a periodicity which can be measured with an accuracy comparable with atomic mass. And this is the fact actually which makes them preferable for using these sources for navigation.
So how do we actually do that? We have these pulsars that we know we can trust. How do you then use those as a means to navigate through deep space?
Well, this goes through the timing of these sources. It's just a measurement and a comparison of pulsar reference. It's similar to the GPS. And this in extent is true and is not true, because in the GPS satellites, the signal which receivers are able to receive and to record has information in the signals itself. And this is not the case for the neutron stars, for the pulsars. For the pulsar signals, they are just emitting light pulses. When the beam they radiate crosses your instrument, your observing instrument, you see a flash or a peak in the intensity in your instrument. And what you are going to do for navigation is just comparing the arrival time of these peaks. And this helps you because you know where the arrival of the peak should be. And then you can compare the phase or the time where the peak arrives, and you compare it with the time it should arrive. And this is a difference. And this runtime difference, so to speak, gives you, if you multiply it with the period of the pulsar, with the velocity of light, gives you the distance difference from where you assume that you are in the universe. And this helps you, and then you correct your position, you continue with the measurement, and you get closer in measuring the pulse where it should be, where you expect it to arrive, and then you have the information that you are at the position you assume you are.
So does this rely on having, let's say we've got this onto a rocket in the future, we've put the technology on there, does this rely on carrying a very large library of these pulsars, and where
it's not software, it's not the effect of the pulsars. This probably can be compressed in a file of less than a megabyte. This technology would have been completely unfeasible because of the weight of the navigation device. So we're using X-rays, and the X-ray mirrors itself of previous X-ray satellites we had a weight of a few tons. So it would be completely interesting to have an instrument sensitive enough to record the and light to use it as a navigation device. I mean, it doesn't make sense if you have a spacecraft which has a weight of 1 ton by itself to give it a navigation device which is 4 or 5 times as heavy.
So what's changed in the technology now in order to enable us to use pulsars outside the positioning system?
This pulsar based navigation became possible with the development of light-weighted X-ray mirrors. And these light-weighted X-ray mirrors are developed anyway for the next generation of X-ray satellites, of X-ray observatories. The one which are in orbit now, so we have mirrors which are quite heavy. For example, 1 square meter of collecting power for X-ray Newton, X-ray satellite observatory which is in space now, has a weight of 2,300 kilograms. And the weight of a comparable new device, if you use, for example, micropore glass optics, is 25 kilograms. So it's a huge difference. But with the old mirror technology, this would have been completely invisible, really.
So how do current missions know where they are in space?
Usually those which are near the stars are use GPS. But the others are all controlled from ground. This radio signals. This is called Dadbod, and DOD stands for Doppler ranging. So there is a radio signal sent to the satellite, and the satellite answers, sending a radio signal back to the antennas. From the runtime difference, you multiply this with velocity of light, you get distance to the satellite, and from the Doppler shifting, small frequency variation in the signal, you get the velocity of this satellite, but just the radial direction, not the overall path in the sky.
Alright,
This
10
open
times 10
tracks the
kilos.
satellites for many days, and then you notice small differences in the angle of your antenna you need to follow the signal. And this then overall gives you the position and the track of the satellite. These are 2 points you can mention is that this method depends on the distance from Earth. Accuracy depends on the distance from Earth. It's roughly 4 kilometers accuracy on the distance from the Earth to the Sun. But Voyager 1, for example, is at 115 astronomical unions, and you have quite a large answer at this distance already. The other point, which is very important, and even the most important one, in my opinion, is that with the pulsar-based navigation device, you have the ability to have autonomous navigation system. It works independent from what's going on on Earth, and everywhere in the solar system and beyond is the same accuracy of few kilometers, a few miles actually. This really makes it great.
Further back up from the Scientific Institute in Munich. This is Naked Astronomy, and this month we're going to a national astronomy meeting in Manchester. Still to come, we'll hear how CubeSats can help us to understand space weather, and we'll discover an enormous tornado on the surface of the Sun. But first, what happened in the early universe? Millimeter wave telescopes are beginning to shed some light on some of the big questions about early star and galaxy formation. To find out more, I spoke to Bram Veneman from the International Institute for Astronomy in Heidelberg, and before him, Richard Whitman from the University of Cambridge.
Well, one of the big questions in astronomy is when do the first stars and galaxies form? And one of the ways to do this is just by looking for objects which are very far away. Because objects that are very far away, in light travel time, we see those objects very far in the past. And last year we found a new quasar with a redshift of 7. When light left this quasar 750 million years after the Big Bang. What we like to do is to measure something into the mass of the galaxy and what's chemical composition is. And in particular, what we're trying to do is when the universe started, the Big Bang, the universe was mainly hydrogen and helium. There were no chemical elements like iron or carbon. So we want to try and look at these objects back and see can we detect chemical elements like carbon, nitrogen, and oxygen now. That tells us about when did the chemical elements in our bodies on Earth first form.
The heavier chemical elements, which astronomers confusingly call metallic, whereas chemists would quite clearly define them otherwise, are said to have formed inside stars. So presumably, in order for you to see these, there must have been at least one generation of stars existing before that in order to produce these heavier elements. 750 million years after the Big Bang doesn't seem like a very long time to have had that turnover of stars.
Yes and no. Stars like the Sun have ages of 5 billion years. However, stars which have a mass of 2 or 3 times more massive than the Sun burn their fuel faster because the gravitational potential of the stars means that the cores of these stars are hotter. And the nuclear fusion reactions that take place in stars which are, say, 10 times the mass of the Sun, those stars have lifetimes of only maybe 10 billion years. So these stars, in terms of they burn fast, die young.
Bram Veneman, you have been working on this project as well. What are the challenges of actually getting information about these? It's so very distant.
The problem is because these objects are so distance shows are very faint. Distance shows are very faint. So what we did is, if you look for quasars, which is basically a very massive black hole where material is warmed up and it's getting heated and shines very brightly. And because it's that bright, we can find it. The problem is that because it's so bright, it's very hard to see the galaxies surrounding the black hole. So the method we use to actually find it might work against us. So we have to find another way to actually see what the galaxy looks like with very bright light from the black hole.
When looking at stars, people often literally place an opaque disc in the way and try and see around the star. I assume you can't do that for enormously distant quasars.
No. So the thing what we've been doing is then we went to a different wavelength machine. We went to millimeter wavelengths where the radiant black hole is not so bright and where the stars and the material surrounding the stars is actually much brighter. So we knew where to look and we use different telescopes to actually look for emission of the galaxy where the black hole sits.
Once you're doing that, you just use standard spectroscopy in order to work out what the material must be.
It's not spectroscopy, but what you get in the end is a spectrum. Only the method is slightly different. You combine the radio waves and you get the spectrum out of it.
Hey.
When you were able to get the spectrum, what did you see?
Hey, poster.
So we saw 2 things. We saw the glow of carbon, which is a sign that gas is cooling, and we saw the glow of dust. These things.
So I basically focus on a upper body, lower body split at the moment.
Because we do see this glow.
So one day lower body, one day upper body.
Means that prior light was emitted, had to be a lot of stars being.
I've kind of been
So not only do you have evidence of a high rate of star formation 750 million years after
the
you also have the evidence left behind
with
that
upper
there's
body.
high rate of star formation before that. So it also helps to
My focus has kind of been
a general understanding of the history of the universe.
dumbbell bench presses, both
Everything we do needs
inclined and flat,
It's almost
um,
something to actually allow for this.
just to kind of
Richard, what does this
increase
mean?
that strength here.
We got this carbon signal back far back. We know that there must have been high rates of star formation then and before it.
lower body,
do to try and answer some more of these questions?
Well, there's a number
I've been having a lot of trouble with my knees
with this particular question.
over the last year or so.
Some other
I
oxygen
injured my right knee at work,
ratios of those elements tell you something about
and so I've been kind of trying to focus on,
estimate the average mass
I
of
guess,
star that went into making this car.
exercises that
Mass of star that went into it.
kind of will strengthen my legs but
This
kind of
type
limit my
information
knees
carried
out a bit. So
very challenging.
doing a deadlift kind of hurts, but like a sumo deadlift with my legs out wide seems it doesn't hurt my knee as much.
Possibly we can find out what the things that make up multiple components. There's one prediction of formation of galaxies is that they form from smaller units.
About 10 years ago, I tore my bicep tendon at work,
Spatial resolution.
and then about 2 years after that, I tore
Research program. 2 years will we find a number.
to the bottom of the shoulder. What muscle? I can't remember the muscle at the bottom of the shoulder blade. But I tore the bottom. So I had a client grab me by the arm and pull me to the ground, and I tore that muscle at the back of my shoulder blade. So I have a bit of trouble with pull-ups and that. So the lat pull down is something I focus on as well now at the moment. Just kind of, and overall just kind of get stronger so I'm around longer for the kids, really.
They also tend to form in very dense cold places in the universe surrounded by dust and gas. What actually happens is very little of this ultraviolet light gets out. Most of it is eaten or absorbed by the dust as interstellar dust grains. So tiny grains of silicon and carbon absorb the UV light, but energy is conserved, so eventually these grains re-emit this light and move into the infrared waves, what we would call heat. So most of this information is hidden and then is re-emitted from the infrared. And then we're looking at galaxies way back in time 10 billion years ago. So as the light comes from these galaxies, it's further stretched to even longer wavelengths. By then, the wavelength of light is about a millimetre, just less than a millimetre. So this is where it's sub-millimetre comes from. So who's new about the scuba camera itself? Edinburgh, the UK, but Edinburgh particularly has a long history of building these cameras. First for the infrared and then for the sub-millimetre. They built a camera called Scuba, which was the world's first sub-millimetre camera and worked in the JCT in the 1990s. This is it's responsible for discovering these distant starless galaxies, distance shrouded. The camera had only, I can't remember, about 40 or 37 or something detectors. To be hand wired in and glued in place because nobody basically built an imaging array in the sub-millimetre. So if like there was no analogous.
I don't know. I don't have enough followers to earn money at the moment.
To build a proper array of like a camera, like a CCD equivalent.
I'd like to build up more followers so that I can start earning money, but I don't at the moment. I don't have anything, like I haven't got enough to monetize even on Twitch yet. I have a feeling I'll make it to Twitch monetization before I make it to YouTube monetization. I do have a, for something else I do, for one of the community TV shows I work on, we do have a coffee account. Ko-fi? No. Buy me a coffee, that's the one. It's not Ko-fi. Buy me a coffee. I just can't remember what the right one is. What the URL for it is.
If you look back over cosmic history, it turns out there was a year lasting about 1 billion years. From about 10 billion years ago till about 1 billion years ago, things were really exciting. It was the kind of Jurassic Park type star forming galaxies when galaxies roamed the universe as they don't seem today, forming stars that are kind of thousands of suns forming these objects. And these most violent star forming objects, they don't exist anymore. Just after their frenzy, they've actually somehow either shut themselves down or black holes and shut them down, so that's a kind of final hurrah, some kind of mad party in the break, basically. So we need to look back to the epoch of this mass star formation. And also these most violent star forming objects do seem something particularly exciting in us. They're the ones that you're actually least likely to see as space telescope and most likely to see this. So it complements rather well what you can do with normal optical astronomy because these are the objects that you can find otherwise. So presumably there's a lot of theories that only now are we going to be able to test. Now we can actually be able to these star forming regions. Yeah, I mean both detailed theories, so follow-up studies can try with ALMA and try and take even higher resolutions of these objects. So the goal of Scuba 2 is really to act as a survey to find these things.
If you go to, there's a website called Libraries. No, sorry, Odyssey. It was Library, now it's called Odyssey.
It's the sub-millimeter galaxies that have proved, you know, the most testing for these models to produce them. The typical picture of galaxy formation in our universe involves some small galaxies merging together into bigger units.
Yeah, my iMac's too old to play games on, so I don't really stream games. I've been thinking about it. Last night I re-downloaded OBS. It seems more complicated than I remember. I've got an Xbox. The kids took this. Oh, sorry, Xbox 360. The kids took the Switch to Japan with them, so I don't have that at the moment. Like I said, I've got the iMac, I've got an old Mac Mini there. It's probably like I can't remember. I bought it in like 2010, 2012, I bought it somewhere between 2010 and 2014. I can't remember when it was. I could probably use that, set that up. Maybe that, I don't know whether that'd be strong enough to take a HDMI signal. Actually, I don't know if can I put a HDMI signal in it? A friend of mine years ago gave me a Elgato, like an Elgato thing that plugs into the computer. But I haven't used, we used it to capture some games. There is a clip, there is a video of Kai on my YouTube channel. There is a video of Kai and I playing a Star Wars game on the GameCube in multiplayer, and how I did it. I set up like the Filmic Pro had that double take app where it records two cameras at the same time. I had one aiming back towards us, one aiming towards the TV. So I could probably do that. I just don't play games as much as I used to. Like, I work during the day in one job, and I work the other every couple of nights. I work in the other job.
Initially the finding that said, well, hang on, there might be something interesting there. What do you think it was aimed at? It's not really aiming at something as such. So we're not talking about stellar alignments. We're not talking about more advanced astronomical alignments there. What we're talking about is something very simple that everyone experiences in their house during a year. You experience how the sun, not during a day, but during a year. And this is something that you can see because this stone is aligned north-south and to such an angle. So the north-facing side, the smoother side, is actually catching the light for the entire day only around its winter half of the year. So actually it's not looking at a very weird star constellation or odd star or something where aliens will visit us in the future. It just is plainly showing us where the sun is in the sky for a certain time.
Why would that be important to presumably they could see what was happening with the sun anyway.
Yeah. The old Mac Minis there with the old Apple TV. I've got like one of those big flat white Apple TVs sitting there.
That's quite important to say that it is not really used for determining when that's
actually no, that was time capsule.
So they had already rituals sent out or meetings.
No, that's the time capsule.
Times of the year. This is the point, and that's
actually, here's the box.
You want to make them special somehow. So you want to mark the page where you need
Mac Mini. What does it say?
So you would place a marker there. You would make it
Model
quite substantial, and having them
A1347.
work together to place it there. And it's not just general marker. You could put a sign of any
Mac Mini 2. Mac Mini 2.4. What's
in this case? It's conveying importance by only illuminated. Maybe it's a midday meeting.
2010. It's got on there. Couple 20. So that's like, what's that? A 16-year-old Mac Mini. Maybe that'll do the work. I don't know. Maybe I can live stream with that. I don't know.
I think that's exactly. It's a tool to emphasize rather than a tool to observe. And I think that's quite important if you try to understand what ancient mankind did at that time.
No, man, that's cool. Keep chatting.
As such, we did sit down and point into the sky and look at how many marks something's moved or rotated or lists of when star rose. We did watch the stars. We understood what happened, and that's ever so clear in many monuments. We knew that already, but this is a nice example that 2000 BC, people had very good knowledge of what was going on in the skies, and we don't have to extend it to the society, but a small group would have known what happened.
The knowledge from 4,000 years ago is sadly lost. So how can we look further into this to confirm our idea of what we think it is and to get a better idea of what would have happened around it. So,
This is where we have to make sure what we've done as facts are facts. So we have to really make sure we are looking at many different angles. Like our project is looking at the orientation of the stone, trying to support it through other packing stones that would show that there's an orientation center of the stone. So we try to eliminate any other things. But we're trying also to see how it fits into the context. What can really help to understand a bit more about the stone and possibly the next step is to explore very deep side of the stone.
There was a guy on, I always watched him on Instagram, but there's another guy, another Australian, he do a lot of React vids, and I think that was mainly Instagram React vids that he was doing, but he recently got a job where it's a huge pay jump for him, like well into 6 figures, deep into 6 figures, and he and another friend of mine was like, well, you send me all these reels that are along those lines, so you should take over for him. You know, just start reacting to Instagram reels and kind of see if you can take over all. And I think maybe I could. All right. I don't know whether it affect my job or not. My job's all right. One of my jobs, we've had redundancy breathing down our neck for 7 years, 8 years. Every year they're like, oh no, we'll keep you on a little longer, we'll keep you on a little longer. And then COVID happened, oh no, we've got to keep you on definitely for COVID. And then after COVID, oh, you know, we're keeping you on, and now it looks like we'll be out of work in the middle of next year. They'll probably finally pull the plug on us next year, but they don't give us any answers. We ask questions, they don't give us any answers.
And those volume injections, they can head into but the mechanism that drives solar storm, we are thinking that these kind of smaller solar storm tornadoes, although they are still quite play some role in triggering those bigger, even bigger.
So weather on the sun is very interesting. Clearly, it can impact us on Earth. It's not just academic. What observations are you using? Where do these observations come from?
It's come from a satellite called Solar. It's very special images and the data, and we just have to mine those data.
So how do we now hope to try and understand this tornado, and what can it teach us?
Well, when we saw this event in October, the minute I saw it, I was hooked, you know, and we've spent the months since then trying to interpret this, because it's a very complex dance of plasma and very hard to interpret and understand. But our hope is to build maybe a model where you see similarities to the true events, and this will help us pin down.
The other thing is, I don't really want to be.
In the true tornado.
We've seen on the surface of the sun.
They might redeploy me to another department, and while I know there's a department I'd love to be redeployed to, the hours that other department keep would not work with my family situation, getting the kids to and from school and that type of thing. So,
I'm struggling really to understand how magnetic fields can form this sort of shape. Do we have some good ideas how it might work?
Well, it's something happened below the surface what we can see. And something happened there, and it's driving this kind of very fast material. So we can follow inside.
And Hugh,
On the surface of the sun, the gas is the boss. It dominates the magnetic field, and it will whip it round whichever way it wants. But sometimes that magnetic field hooks out into the atmosphere, so it does emerge from the surface of the sun as a typical field.
so what do we need to do now to better understand this tornado that you see, but also to keep an eye out for new ones or similar weather activity on the sun?
Keep on looking at SEO data. Hopefully have other missions looking at such detail. And it's kind of important to develop computers to look at the data for this type of stuff automatically. We're lucky that we saw this event. Could have missed it.
Hugh Morgan, and before him, Xing Li from the University of Aberystwyth. And their lucky discovery will help us to understand solar storms, which lead to coronal mass ejections that are a component of space weather, which is a hot topic in astronomy at the moment. One new mission called Cinema hopes to add to our understanding of space weather using 3 tiny CubeSats with innovative Professor Tim Horbury from Imperial College London was involved in developing one of Cinema's sensors to find out concept called magic.
Cinema is really about trying to understand space weather, so the idea about how the sun affects the Earth. Cinema will go into a lower orbit than the orbit that the International Space Station is in a few months. And what it's trying to do is measure the radiation belts around the Earth, so that the space around the Earth is full of very fast moving particles, which can knock into space weather and damage electronics, damage astronauts. So it's something that's actually technologically important. So that's one of the key goals, is understanding how those radiation belts are formed, how the particles are accelerated up to high energy, and how that affects the rest of the space environment.
Cinema consists of 3 CubeSats, and so far they've been mainly used as a test bed to test technology, test scientific ideas, but not often for real science. So what's changed?
The CubeSats form factor, whole idea skills they need to go into space program. What's changed really is that people have realised that actually the technology is getting good enough to build really capable instruments. So the CubeSat that we're involved in, the project is called Cinema, and that CubeSat is huge compared to most CubeSats. So it's only 30 centimeters long. So it's really pretty small, about 1 kilograms, so it seems to be. But in fact, within that very small space, we have two really world-class science instruments, as well as all the kind of gubbins that you project. So it's actually quite a grown-up project compared to a lot of CubeSats. It's building real science in space. But as a result, it's had to be quite sophisticated in the way that it runs, and that means that the University of California, Berkeley, who actually designed the spacecraft, have had to work really hard, and it's taken quite a long time to develop all the technology all over again, really, to build a spacecraft that's really small.
You said that there were two instruments in there. What are they, and what particular aspects of this question are they going to ask?
Right, so the instrument that's being built in Berkeley, in the University of California, is called STEIN. So STEIN. That stands for Super Thermal Electron Ions Neutron. So it's actually a very clever little instrument. It's very small, and it can measure 3 different things essentially at the same time. It can measure very fast-moving protons, which are flying around in space, and for example, coming down and hitting the top of the Earth's atmosphere, just using your raw gun. It can also measure very fast-moving electrons. The key thing that's really impressive about this instrument, it can also measure neutral particles that fly around basically, and they're generated in a very interesting way from the radiation belt. When a fast-moving particle from the radiation belt hits a neutral atom far up above the Earth's atmosphere, it can basically swap an electron and end up going very quickly as a neutron. And what that means is after that point, it goes in a straight line and can then hit this detector straight on. So by looking, we're essentially using those energetic neutrals to build up a picture of what the radiation belts look like for these neutral atoms from our view. So Cinema will actually fly around close to the Earth and peer upwards and look at these particles raining down over the top of the radiation. So that's the STEIN instrument with these particles. The other instrument is actually built at Imperial College, and that's our college. And that's an instrument called a magnetometer, which measures the Earth's magnetic field. So we've been building magnetometers for years at Imperial College, and they're flying the spacecraft throughout the solar system, around Saturn, around the Earth, all over the place. But the instrument that's flying on Cinema is much smaller than what we build. It's actually using technology called magnetometer. So if you've got a hard drive in your computer, the little read head that measures what's going on in the particle itself is actually a magnetometer sensor. So they're very, very small. The solid state becomes very rugged. And so we can build a sensor that's actually a 2 centimeter cube. It's incredibly small, very, very small. And so that will measure the Earth's magnetic field. And in fact, the magnetic field itself isn't constant. And that's actually the effect of the solar wind from the sun. It's actually squishing the magnetic field. By looking at those very small scale variations, which actually are very, very small, possibly very tiny, very small, we can actually learn quite a lot about how solar wind is affecting the Earth's magnetic field, and actually how that's accelerating these particles.
Space weather has been quite a hot topic for a little while now. There are quite a few large-scale missions that include things to look at space weather, so for example, the particles coming from the sun. So what gap does Cinema fill? What are you getting from this CubeSat that you're not getting from the bigger mission?
Right, yeah, I think that's a very good question. Cinema actually fills a really important gap in the chain of information from the sun all the way to the ground. So we can look at the sun and see things happening like a flare going off at the sun. We can measure the sun's time in space and see like a big foreign mass ejection coming from the sun that's going to hit the Earth. We can measure as that hits the Earth's magnetosphere and the sort of magnetic environment around the Earth. And then we can actually measure things down on the ground. There are various diagnostic instruments we have on the ground to measure, say, how the Earth's magnetic fields affect. But actually, there's a crucial step in that chain we don't have, and that's really just above the top of the atmosphere. So we need to make that extra connection to try and understand the full flow of information all the way from the sun down onto the Earth. And actually, those variations that finally come down onto the Earth's surface can actually be really important. So they can affect, for example, radio communication. They can actually affect things like power lines and whatever. We've had big power outages in the past because of the electric fields that are generated in the Earth's surface by the variations by the space weather. And so actually, Cinema will produce that crucial extra step between the ground and space.
And what do you have to do with the data? And what do you have to do with the data that you're collecting? How do you see it informing future research or helping us to understand what happens down here on Earth?
I think Cinema and the 3 spacecraft together are really going to help as part of this chain of information. So it's not just about those spacecraft by themselves and the data they get by itself. It's about putting that in with everything else. So the session that I'm talking in this afternoon is actually about a mission called SWIRM, which is a 3 spacecraft mission which is flown by the European Space Agency. And it's really to measure the internal magnetic field of the Earth. But that field that you measure in space is greatly affected by the space weather effects. And so actually we see Cinema and in particular the magnetic field instrument magic as providing extra information that we can actually help to inform the swarm data analysis and combine it with all these other instruments to actually learn more about space weather.
Tim Aubrey from Imperial College London. And that's it for this National Astronomy Meeting special. Join us next time on Naked Astronomy when we catch up with your space science questions. So if there's anything you'd like to ask, email astronomy@thenakedscientists.com. You can also follow The Naked Scientists on Twitter, that's @NakedScientists, or join us on Facebook at facebook.com/TheNakedScientist. This one is produced by me, Ben Valsley, for The Naked Scientist, and from Cambridge University, with support from the Science and Technology Institute.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy. With the BankWest single-use virtual card, your card details disappear after use, which means less time worrying about fraudsters and more time worrying about sleep, alternative milks, captcha screens, and having to talk to other parents. BankWest. With the BankWest single-use virtual card, your card
And it dominates the magnetic field, and it will whip it around and toggle it whichever way it wants. But sometimes that magnetic field then pokes out.
People have realised that actually the technology is getting good enough that you can build really capable instruments that are small, that stands for Super Thermal Electron Ions Neutron. So it's actually a very clever little instrument. It's very small, and it can measure 3 different things essentially at the same time. It can measure very fast-moving protons, which are flying around in space and, for example, are coming down and hitting the top of the Earth's atmosphere to produce the aurora. It can also measure very fast-moving electromagnetic radiation, but flying on that's actually on the ground, fields that are generated in the Earth's surface by the variations by space weather. And so actually cinema will produce that crucial extra step between to the internal magnetic field of the Earth.
So if there's anything you want to ask,
.com/ability criteria apply. Consider the TMD and PDS or TNCs available from Bankwest.
From professionally designed or DIY investment options, it's never been easier to start investing. Search investing in the Sunbank app. Investing carries risk. Consider the T's and C's and PDS where applicable, and fees and charges before deciding.
Thrusting space science into the audio dimension. This is Naked Astronomy.
when did dark energy become the dominant force in the universe? In this month's Naked Astronomy, we look back at the history of our expanding universe to find out when gravity lost its grip.
One of the key things is that we're looking at that expansion at a time when this dark energy, this dominant component, became important. So we're looking at a redshift of 0.57, which is about when this dark energy started to dominate, about when the universe started to accelerate. And that's a key time to try and understand the universe.
We'll also be examining the global trade of meteorites to explore the tension between scientists and collectors, and answering a number of your questions. I'm Ben Vanson, and this is Naked Astronomy.
Supported by the STFC, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
First, I'm joined by Karen Thorpe, Andrew Ponson and Dominic Ford for a look at this month's space science news.
Well, this is a paper in the monthly notices of the OAS, which sheds some light on how galaxies evolve. Now, the galaxies that we see in the night sky fall broadly into various categories. The most obvious species groupings are that some galaxies have spiral structure, like our own galaxy, and others have elliptical structure with no arms in that elliptical structure. Now, there are also differences in the physical makeup of galaxies. Some have lots of gas, which they seem to be actively forming into stars, and others seem to be more or less gas-free. And that leads to the question of whether these are fundamentally different populations of galaxies, spirals or ellipses, or whether they're different evolutionary states, and whether, for example, spiral galaxies evolve into elliptical galaxies. Now, there's a fairly firm consensus that these are evolutionary states. We see examples of merging spiral galaxies that we think will fall into elliptical systems. But that leads to the question of what happens to the gas, because spiral systems tend to be these systems which are actively forming stars out of gas, while elliptical systems tend to be relatively gas-free. Now, although we see a lot of merging systems, we don't see many that seem to be in the process of flushing their gas out, so we know much less about how that process happens. In fact, I think there are about 5 examples that we've seen of galaxies that seem to be in the process of flushing their gas out as we observe them. Now, Ananda Hota, writing in the monthly Nature, presents images of one of these 5 galaxies, NGC 3841, at many different wavelengths of light, to understand exactly what's happening in this galaxy. And for a start, he sees that many of the stars in this galaxy formed only a few 100 million years ago. So that suggests very recently the galaxy was still forming stars. But today there's only very little star formation in the galaxy, and that is only the outskirts of the galaxy. Now if you look towards the centre, you see evidence of lots of recent supernova explosions, which look like they've been blowing the gas out of the centre of the galaxy. And you also see there's an active nucleus that seems to have turned on. So gas is now falling in onto that central black hole, forming jets, and those jets are flushing the gas out of the centre of the galaxy. So the idea here is that already the star formation is turned on in the centre of this galaxy due to supernova explosions and the active nucleus, but it hasn't yet reached the outskirts of this galaxy, which will probably turn on in about another 100 million years' time. So he's dubbed this cosmic leaf blower. It seems to have turned on flush gas out of the centre of the galaxy, but not yet quite turned off the star formation in the outskirts.
Wouldn't the presence of lots of gas being buffeted and pushed together by the forces of all this, would that actually give you an area that's fertile for more star formation?
It certainly can happen. Supernova explosions can trigger other nearby star formations to form stars. That's called sequential star formation. But if you've got too many of these explosions, you just flush the gas completely out of the galaxy into space.
Karen, what have you seen for us this month?
Well, I'm coming much closer to home and going to talk about a nearby star. It's a very well-known one. It's one of the brightest ones in our solar system. It's Comet, and it's 25 light years away. It's a very young star. It's in a fraction of the sun's age, and it's about twice as massive as the sun. It's surrounded by an immense debris disk that's over 20 billion miles across from the Earth. And that was discovered in the 1980s by the radio mission. And subsequent observations of the Hubble Space Telescope revealed that there could be a planet orbiting just inside the debris disk, with a very sharp inner edge to it, which suggests that it's collecting and guiding the particles, not just keeping the neat over the ring. In fact, whether that planet is there or not is being easily a subject of contention and is unresolved, though obviously very recent observations with the new radio observatory ALMA suggest not just that large planet is there, but there could be a further one outside the debris disk, which is also shepherding the outer part of the ring. However, the result I'm looking at the actual content of the disk, where those came from, and this comes from Herschel Space Observatory
direction. So this is done in infrared.
toe.
And colleagues at Leuven University. And actually looking at the nature of the dust, because
Yeah, I should wear shoes.
suggests that the grains in the dust are both smaller than this, so perhaps only a few millionths of a meter of dust. And actually aggregated together into quite large fluffy particles. And the properties of this dust are similar to what is liberated from comets in our own solar system. So not from asteroids, but from comets. And so they're suggesting that this fusion that we use is created from collisions of comets. And it's an interesting idea, not least because there's an awful lot of these collisions going on. These dust particles, these aggregates dust particles, are very light and fluffy, easily pushed right out by the radiation pressure from the sun. So to maintain this disk has to be continually replenished by lots of cometary collisions, maybe a couple of thousand in a day even, which suggests that this whole debris disk is like an version of, say, our Kuiper belt in our solar system. A huge population of comets all crashing into each other and liberating these particles.
So, are there other similar disks that we can look at elsewhere to try and do some comparisons and work out if it really is likely to become something like our own Kuiper, or in fact to give us more of an idea of what it really is like?
There are several disk systems around nearby stars that we've resolved, usually from scattered light from Earth or again the thermal infrared emission. This one's unusual in that it's actually tilted towards us, so we get a good view of it. We're into further edge on systems which have been studied, say, the Hubble Space Telescope, and those are much more of the interest of actually looking at the condensations within the disk and finding protoplanets forming within that disk. This system around Fomalhaut seems to be at a slightly different stage, and maybe some of the planets have already formed, and what's going on within the disk is showing us a different aspect of the solar system forming around the star.
What does it tell us about formation of comets and the movement and action of comets elsewhere, if it is actually made up mainly of cometary dust instead of planetary or pre-planetary dust?
I think it's telling us something about those very early stages of planetary system formation. So when the comets and material are being flung out from the centre of the planetary system, it's kind of getting us at that space 200 million years after the star was formed, and it's just giving us just that snapshot in time for when lots of dynamic things are happening within what we call the Kuiper belt around our system.
Thank you, Carolyn. Andrew, finally, what did you have for us?
Well, I spotted a quiet announcement by NASA that their Kepler spacecraft has had its mission lifetime extended through to 2016. It was originally going to be decommissioned at the end of this year. Now, just to remind you, Kepler is this spacecraft that has a telescope on it staring at the same stars continuously and looking for signs of planets around those stars. And it's been immensely successful, almost to the point where announcing new discoveries of new planets is getting boring. The latest catalogue was released at the end of February and has more than 2,000 possible planet detections. Now, those are just possible planet detections until other telescopes follow it up and check that there really is a planet there. We don't know for certain. But so far, based on follow-ups that have been achieved, we are pretty confident that more than 90% of those candidates will turn out to be real planets. So we're absolutely inundated with planets now. Now, the point is that one of the original design goals of Kepler was to find Earth-like planets and get some handle on how many Earth-like planets there are out there. But those Earth-like planets have two characteristics that make that tricky. First of all, they have long orbital periods, something like 365 days. You have to wait that long before you see the signal again, because the signal that you're looking for is the planet coming in front of the star. That can only happen once every 365 days. And the other characteristic of our Earth that we're looking to match is that it's something that's quite small, which makes it quite hard to detect. So you want to see it come in front of the star several times to be sure.
Another 10.
Star several times to be sure you've actually seen something, and that means you have to wait for several years. So originally, this mission was planned at the end of 2012. That would have been about 3.5 years after it launched. You might think that would be enough to get a few times for one of these Earth-like planets to happen. The trouble has been that the stars themselves have more intrinsic variability in their light than was originally expected. So that's an interesting discovery about stars. In fact, there's just something about this. So the stars themselves are bubbling away, and that makes it harder to tell whether a little blob that you've seen in the amount of light from the stars is genuinely because of a small planet like the Earth. And so the science case for extending the mission is really compelling, because transits to see something like the Earth. We still want to do that. It's not automatic though, because although Kepler is there sitting in space, it still costs money to have people analysing the data, and instruments do degrade over time. So this had to be looked at carefully, but NASA came to the conclusion that it was worth extending the mission, so it will now go on through to 2016.
One thing that I've always wondered with looking at the transits, where we are just looking at a dip in the light, what is it that causes the stars to be variable without a planet?
Well, there are natural processes that go on within stars that cause them to vary the amount of light coming out. Things like sunspots, or just the fact that the whole star can be wobbling about and varying in size, can lead to signals that can be confused with the transit of the planet.
And on the topic of exoplanets, Andy Masters wrote in to ask if we could see the light from the night side of a transiting exoplanet. Could we use that to look for evidence of life?
As Andrew says, we certainly know of a lot of these planets now. I checked on the internet this morning, and the tally seems to be 763 confirmed exoplanets as of this morning. And as Andrew says, Kepler has got about 2,000 more candidates, where it just needs to see one or two more passes of those planets in front of their parent stars before they can be confirmed. But in all of these cases, we're only seeing the indirect influence of these planets on other objects around them. Either, as in the case of Kepler, the planet is passing in front of its parent star and causing a dip in the brightness of that star, or we're seeing gravitational influence of that planet on its parent star. Now, what we would really love to be able to do would be to see the light actually form that planet. We would then take a spectrum and we would find out the position of those planets, we could find out whether they have atmospheres, and we can start to ask questions like how habitable they might be, or whether they've got oxygen and water and things we think we need for life. The problem with seeing the light from these planets is that their distances from their host stars is absolutely tiny compared to distances of the host stars from us. So when we look at them on the sky, they're very close on the sky to stars which are very much closer than the planets. So if you were to take a Hubble Space Telescope in one of these systems, the star and the planet would be about 1 pixel apart in that image, but the star would be 1 billion times brighter. So it would be completely different from the glare of its parent star. So I was trying to work out an analogy for this. And the best way to come up with it, you've got a lighthouse, and you've got a candle 100 centimetres away from the lighthouse. You look at that with the International Space Station. The candle is actually 100 times brighter than the planet would be that you were trying to make out next to the lighthouse. So people have worked out how you can try and see this. And there have been 2 proposed missions, one by ESA and one by NASA. And you would need to fly about 6 telescopes similar in size to the Hubble Space Telescope in the constellation about 100 metres apart. And you would need to bring all of their light to a common focus to form an image. The problem with that is that it's incredibly expensive. And so both of those missions, Darwin and the Terrestrial Planet Finder, it was completed in 2007, were basically too expensive to fly. Now, I hope at some point those missions will fly, because I think this will be a tremendous step forward towards knowing whether there are other habitable planets out there. But I think probably, to be honest, it's going to be 20 years, at least, before they would actually make it into space.
And it suggests that we could be looking for specific signatures, like, for example, the light from sodium roads. So if there's lots and lots of roads and they use the same technology that we use, there would be a spike in the particular signature of sodium. Would that just be lost in the noise of the planet? Is it really that insignificant?
The problem is stars also have sodium in their atmospheres, and as I say, they're about 1 billion times brighter, so it would just be lost in the noise.
And of course, as with all astronomical observations, we're looking at a certain period of time, depending on how far away these things are. And that brings me to this question from Robin Freestone, who asks how long Earth has actually been habitable.
Well, it really depends what you mean by habitable and by what it might be habitable. I mean, if you think about it, the Earth formed about 4.5 billion years ago, and an awful lot has happened to that Earth to render it habitable. Because the very early Earth that would have formed from the solar nebula would have been molten, incredibly hot, undergoing intense volcanism. And there wouldn't have been any oceans, no liquid water, until you have this heavy bombardment phase of our own solar system where we think, we need to deliver water, deliver the oceans to the Earth. That happened about 4 billion years ago, and 8 billion years ago. And then you've got to wait till the Earth has cooled sufficiently to hang on to that water, and then we start to develop oceans, which is where all life began. So you could say, in terms of single-celled life, and even sort of multi-celled life, you're looking at, say, well, single-cell about 3.8 billion years ago, multi-celled life about 1 billion years ago. But the Earth still strictly, I wouldn't describe as habitable at that stage, because you've got an atmosphere. The primordial atmosphere is incredibly toxic. You need the oxygen in the atmosphere, and that begins to be addressed. Begins to be addressed once you've got oxygen-producing life forms, such as the early stromatolites, for example. And so it takes a long while to produce the kind of atmosphere, the kind of ocean, the kind of Earth we've got today. And so my best guess is that we would only begin to recognise the Earth as habitable about 500 million years ago. And it's at about that point you begin to get the ancestors of today's insects, today's animals, mammals turning up perhaps 200 million years ago, and primates only about 65 million years ago. So it's only relatively recently within the Earth's history that I would describe it as habitable.
It seems something of a contradiction that in order to be somewhere where life could develop, we need this incredibly destructive heavy lava just to provide the water.
Yes, well, the provision of water is a crucial stage in the formation of life, and there is still debate about whether the comets that live in this water will come from in the primordial solar system as well. It's still not completely understood or proven that this was the case.
Caroline Crawford. We'll have more of your questions later on, but if you have a question to put to the team, astronomy at the Naked Scientists, or tweet at Naked Scientist.
This is the difficult one.
The universe is expanding at an accelerated rate, and the driving force is the mysterious dark energy. But this hasn't always been the case. Earlier in the universe's history, gravity dominated, holding all the matter together. Using data from the Sloan Digital Sky Survey 3, and international time researchers looked at the distribution of galaxies for evidence of it. When the universe was very young, it was almost like a liquid, and acoustic or pressure waves established clumps in matter. This grain structure then became frozen as the universe aged. Since then, the expansion of the universe has stretched out the waves. By looking at the distance between clumps of galaxies throughout the universe's history, we can map out the expansion of the universe, including pinning down the time when the first came to darkness. To find out more, I spoke galaxy. Will personally actually to share it from the universe afterwards. Roughly 15 years ago, it was announced that the universe is accelerating. Since when, a lot of cosmology has been trying to understand this acceleration in a lot more detail. That was what this project was actually designed to try and do.
So it's a very big question. How do you go about answering it?
As it turns out, there are a number of ways. And one of the things we're trying to do is just get more observational evidence of exactly how the universe is accelerating. We do that in two key ways. One is to get more information about the actual expansion rate of the universe and the acceleration itself, so how much faster things are moving apart than they were in the past. The other tack that we can take is to look at structure formation of the universe. So galaxies are not distributed.
No one from.
clumped together.
No one's dropping in from Kicks today.
And the rate at which it grows is related to
Oh well.
accelerated expansion of the whole universe. You can imagine that if the universe is accelerating a great deal, then it actually stops.
Well, nobody from Kicks commenting. Hey, if you're watching on Kick, just let me know.
The accelerated expansion and structure growth within it is a really good way of telling apart some of the key models for the accelerated expansion of the universe.
And what's the technique you're
Can you-
actually using to measure these distances and the changes over time?
Okay, so the technique is called barioacoustic oscillations. What these are?
Hello.
The results
I've got to keep checking the camera for the Kick responses. So I've got YouTube and Twitch here on the iPad.
and they set up a
I just
particular
gotta-
distance, which was the distance these waves
Yeah,
get
just
to.
got to go look
So it's rather
at
like
the back
if
for
you imagine
Kick.
the universe is a pond, and you drop the universe is a pond, and you drop a pebble in that pond, then if you measure how far this wave that's resulted when you drop your pebble has got to at different times as the universe is expanding, what you're actually doing by making that measurement is mapping out the expansion rate of your pond or the expansion rate of your universe. So that's the fundamental physical process that forms these barioacoustic oscillations. And when you have a galaxy map, you can actually pick up this wavelength by looking at pairs of galaxies. And then statistically, you actually get excess in the number of pairs of galaxies separated by the distance that the wave has travelled to. And we are fundamentally picking up the residual of this acoustic wave. We're picking up at different times in the universe expansion. And from that, we measure accelerated expansion.
Rita, what observation are we What are we using to look at it?
The fundamental observation is the position, the three-dimensional positions of 250,000 galaxies. So these galaxies are now distributed uniformly in the universe. So some parts of the universe are more, some are less. And it turns out that the particular pattern that they form tells you a lot about the content of the universe. Because if the universe had a different content, more matter, less matter, it had been expanding at a different rate, then you'd see a different map of galaxies. So the fundamental observation is this.
Does this map not purely tell about the matter? And if it's the dark energy that's the force that's causing the expansion, don't we need to find some other way of looking that doesn't just look at matter?
Well, there's two ways to answer that. First of all, you're right. This map tells you, to be honest, even when I'm saying I'm mapping 250,000 galaxies, that's only a tiny bit of matter in the universe. We know most of the matter in the universe.
Alrighty.
Matter that we can't see. But by and large, these galaxies trace it. So if you see more galaxies in
So
but if you make this observation,
this will be.
distances from you, you're actually
This is
looking
my
at
last set
this happens
for the
because
night.
light takes time.
Then I'm
to
gonna
travel from
sign
galaxy.
off.
So if you look at a galaxy that is 2 billion light years away from you and one that is
I won't be
8
streaming
billion
tomorrow.
light years away from you, by looking at how
I've
these
got,
distances pattern has changed between one and the other, it tells
got
you
quite a
how
few
long
errands to run tomorrow.
in that space of time.
How does this fit in with
At least I don't think I will be streaming tomorrow.
where we first confirmed the universe was expanding? The results that you're getting now, do they
Odds are
fit
not
into
quite zero,
we started to contradict the theories that we already had?
but they are pretty low.
Actually, what we're seeing is
Streaming
actually looking
tomorrow.
at more detail at the expansion of the universe. We're seeing it just has
Saturday.
richer and richer,
Yeah, I'm not too sure yet.
it's still expanding. So Hubble better
Sunday,
And we can
probably
use
more
that
likely streaming
to
Sunday.
accelerated expansion to build a full picture
Yeah.
of this expansion this expansion through cosmic time. And one of the key things about this project we're talking about is that we're looking at that expansion at a time when this dark energy, this dominant component, became important. So we're looking at a redshift of 0.57, which is about when this dark energy started to dominate, about when the universe started to accelerate. And that's a key time to try and understand the universe.
So if we were to look back, what would be the expansion of the universe? Has it always been expanding at an accelerating rate? It sounds like we had a long period where actually it was the gravity, the matter, and the dark matter that was more important than the dark energy that's causing this expansion.
Yes, that's correct. Well, the standard model for the expansion of the universe, different components of the universe come to the fore at different times. So actually it's the radiation that dominates the expansion rate of the universe. And the universe is full of light, and that light initially is the energy density. Then later on the matter becomes the expansion. And that's when you start to see the deceleration of the universe, gravity dominating for the material. And now we're in the think of this dark energy, and we're seeing it accelerating.
Do you think there might be another era in the future, or is this it for the universe now?
You're asking me if there's some unknown out there.
But how are we going to take this forward? Now that we've sort of identified where we think, or rather when we think it was the dark energy became the dominant factor,
how could we move forward and understand this further?
So that's a good question. So we've found a new component of the universe, and we're sort of picking and prodding and trying to see how it behaves in different scenarios or different times. The next thing is to get better measurements of these distances and try to see. We have a number of theories of what could explain this acceleration, and what we really want to do is to find the theory that best fits the set of observations that you've made. And so the better your observations and the wider range of observations that you make, the better it is.
Rita Teixeira, and before her, Will Percival from the University of Portsmouth. Dark energy and dark matter are subjects that inspire many questions sent into the show, and Evan Stanbury wrote in recently to ask if the presence of dark matter constantly moving through us and interacting only by gravity might be interfering with our ability to measure the universal gravitational constant, or Big G.
Alright,
Right, well, let's just take a step back and see what we're talking about.
alright, well,
What this Big G
that's everything for today.
is something that tells us how much gravitational force
oof.
we get for a fixed amount of stuff according
Hey.
to gravitational laws developed by Newton and Einstein. So it's just a number. We've got to measure it because we can't calculate it from our theories. And so you have to come up with experiments to do that. So something you might try and do is measure how quickly do things fall to Earth under the force of gravity, and that would tell you the gravitational force due to the Earth. But on the other hand, we don't then
Alright, so
what the mass of the Earth
be good night
is.
for me.
That wouldn't give us
Oh, the camera's a bit low.
working out what this relation ratio from the mass of the Earth to the gravitational force.
Do the subscribe, the likes, and whatever. Blah blah blah. Otherwise, good night, and I'll talk to you all again soon.